Okay, thank you for the organizers for this very nice invitation. Again, as Giuliola said, I wish I was there, but as we all know the situation. So this is, I'll be talking about joint work with Yu Deng from the University of Southern California, who was also a collaborator of Andrea on the impressive work that she just told us about. So I'll be talking about the full derivation of the wave kinetic equation for NLS, and what we will be discussing is falls under the umbrella of Hilbert's sixth problem. So which asks, so the Hilbert's sixth problem asks for the axiomatic derivation of the laws of physics from first principles, and a main example of that is justifying the laws of statistical physics, starting from the laws of dynamics, taking those as first principle. So as we all know, the statistical laws govern macroscopic quantities like temperature, pressure, or fluid velocity. And those are things that are typically time irreversible. You can think here of the second law of thermodynamics. On the other hand, the dynamical laws, or our first principles, these are the things that cover microscopic quantities like trajectories of or orbits of Hamiltonian systems, for example. And these are typically reversible in time. Here we think of Newton's laws, we think of Hamilton's equations, etc. And the problematic comes from this passage from the reversible to the irreversible, which comes as a result of a series of averaging and limiting operations that creates this arrow of time. What we will be interested in is the rigorous justification of this passage from the reversible to the irreversible. So the classical example here, or the first triumph here, if you like, is given by Boltzmann's kinetic theory, which is something that was suggested by Hilbert himself to pass from the macroscopic to the macroscopic through an intermediate scale, which is the mesoscopic scale given by the kinetic theory. So as Sergio did an really excellent job on Monday explaining this slide in detail. So let me just, I'll be very brief here. So Boltzmann's kinetic theory, it says that if you start with a system of n particles, each of radius r undergoing elastic collisions, then one can derive an effective equation for the one particle density functions, which you can denote by Fn super 1. So this is the one particle density function you can obtain by integrating over the n-1 particles. And namely, the Boltzmann's theory says that the effective dynamics of this quantity is exactly given by Boltzmann's celebrated equation, which is given over here. So this is the right-hand side, which has a transport term. And the left-hand side, which has a transport term. On the right-hand side is the collision kernel, which I don't write explicitly here. And of course, the justification of this approximation was a big challenge, and it was finally done by Lanford in 1975, and was later properly understood, and the proof was properly completed by the authors that are mentioned here, particularly the work of Gallagher, Saint-Amand, and Texier. So what does Lanford's theorem say? It says that Boltzmann's equation, this equation, appears as an effective equation for the one particle density functions in the limit when you take the number of particles going to infinity and the radius of the particles going to 0, but you don't take those two limits arbitrarily. You take them according to a certain scaling law. So this notion of scaling law will be important for us later on. Scaling, which is given by the Boltzmann grad scaling law, which says that n times r to the d-1 is order of 1. So this is called the collision rate, as Sergio explained to us on Monday. And then in this scaling law, or this limit, the approximation of the one particle density function with the solution of the Boltzmann equation over here is justified in the limit as n goes to infinity and r goes to 0 up to times that are order of rho inverse. And this kinetic framework has been highly successful and highly informative and was extended to many other particle systems. So given this success and its importance, the 20th century physicists drew a parallel theory of statistical mechanics for nonlinear wave systems. And here in this setting, we'll be interested in Hilbert's problem for wave systems. And here the microscopic dynamics is given by a nonlinear dispersive PDE rather than being given by Newtonian particles. And so instead of a large number of particles, we have a large number of waves that are interacting with each other. And those waves are represented by Fourier modes on a box of size L. And the size of the box L will be going to infinity, or the number of waves, if you like, will be going to infinity. And these waves undergo collisions through the nonlinear interactions that are given by the nonlinear dispersive system. Okay, so in what follows, we would consider the nonlinear Schrodinger equation as a prototypical example of a nonlinear dispersive equation. So this is, we'll consider the cubic NLS equation written over here, and we'll think of it, this is posed on a box of size L or a torus of size L in D dimensions. Okay, so this torus of size L can have different aspect ratios. So it's given by L, the dilation by L of this fundamental domain, if you like, 0 gamma 1, 0 gamma 2 up to 0 gamma d. And these gamma 1 up to gamma d are the aspect ratios of the torus. We say that the torus is irrational if gamma 1 up to gamma d are rationally independent, which means that k dot gamma is different from 0 whenever k is an integer vector that is non-zero. And we say that this torus is generically irrational if not only it's different from 0, but we have a Diophantine condition that is imposed over here. Okay, and of course one can think of those solutions as periodic solutions on RDs. These are solutions with period order of L, and this L is diverging to infinity. And these solutions of interest for the kinetic theory are the ones where the total energy on the box diverges as L goes to infinity. So we'll be talking the framework that we'll be setting ourselves in, is a framework in which solution, the total energy of the solution diverges with L, but the local energy is finite. Locally in space, this local energy is finite, and this is typical in thermodynamic limits. Of course, just like any other statistical theory, the aim of, or the ultimate aim here is to understand the long-time behavior of solutions. And if one tries to understand the long-time behavior of solutions from deterministically, this is practically impossible. And this is due to the rich set of possible behaviors, long-time behaviors that can be sustained by the cubic NLS equation, or for that matter, any nonlinear dispersive system on a compact domain. So you can see periodic behavior, you can see quasi-periodic behaviors, you can see solid-harmonic behaviors, you can see growth of Sobolev norm type behavior like Giliola explained. So there's a zoo of possible behaviors from a deterministic point of view. Now, even if you set the problem on RD, and if you think of finite energy solutions on RD, then in some cases you have a good understanding of the asymptotic behavior. So for example, you might, for the equation that I wrote in dimensions, say 3, we know that the asymptotically solutions scatter as t goes to infinity. However, the intermediate time behavior of large solutions is not. And this is something that the kinetic theory also can shed light on. It's actually a fascinating fact that we can understand the asymptotic behavior on for finite energy solution on RD without understanding the intermediate type behavior. So, and as such, just like for particle systems, a statistical approach is needed to understand the behavior of generic solutions in this setting. So that's what we'll be trying to do. So for that, let me start by talking about the parameters of the problem. So in addition to, we already encountered one of the parameters, which is the size of the domain or the size of the box. The other parameter is the characteristic size lambda of solutions. So in order to emphasize this characteristic size, we will adopt the ansatz V equals lambda U and think of U as having size 1 in L2 norm. The L2 norm is conserved by the equation. So this is a reasonable ansatz, if you like. And the equation satisfied by U is exactly essentially the same equation satisfied by V, except that you have a lambda squared in front of the nonlinearity. So here as well, I rescaled space so that I'll be working on the standard torus of size L, or if you like, the square torus of size L, So this is L01 to the D with periodic boundary conditions, except that you pay for this by twisting the Laplacian a little bit. So instead of the usual Laplacian, you twist it by those parameters beta 1 up to beta D, which stand essentially for or represent the aspect ratios of the torus. Okay, so this is the equation that we will be playing with today. Now, instead of phrasing, by the way, please feel free to interrupt at any time and ask questions if I'm going too quickly. So instead of phrasing the results in terms of these parameters lambda and L, I will replace the parameter lambda by another more convenient parameter, which is alpha equals lambda squared times L to the minus D. And this alpha will stand for the characteristic size of the nonlinearity. Why is this the characteristic size of the nonlinearity? I can explain it heuristically at this point, but can be justified rigorously throughout the proof. And the reason for that is the following. If you think of a generic solution in L2 that is normalized to be to have size 1, then with high probability, its L infinity norm is order of L to the D minus 2. This is just a statement that with high probability, such a field does not have too many spikes, if you like. And as such, if I look at the nonlinearity and measure it in L2, I can put one copy of U in L2 and two copies in L infinity, and I get that this is bounded by lambda squared L to the minus D, which is what I defined alpha. But for now, I'm just defining this alpha in order to replace the parameter lambda, just for convenience. Okay, so again, let us, just like in the many particle case or in the Boltzmann setting, we start with a random distribution of initial data. And this corresponds to taking random independent Fourier modes for the initial data U initial. Okay, so we take the initial data of our NLS equation to be U initial. So we expand it in its Fourier representation. Here, note that K ranges over ZD sub L, which is L inverse ZD. So this is the lattice with mesh L inverse. And this lattice, when we take the thermodynamic limit, will converge to a continuum as L goes to infinity. Okay, and so what is important here is how we take our Fourier modes. So the initial Fourier modes are given as follows. So they are given by the square root of n initial, where n initial is a Schwartz function that will eventually play the role of the initial data for our kinetic equation. Okay, so these are, and then we multiply that, we randomize those Fourier modes by multiplying them by IID normalized Gaussian variables. So those eta k of omega are IID normalized Gaussian random variables. Okay, by the way, we don't need to take necessarily IID normalized random variables. One can replace those eta k by, for example, random phases. So things of the form, things of the form, so these can be either IID Gaussians, or they can be of the form, for example, e to the I theta k comma omega, where theta k omega is uniformly distributed in 0 to pi. This is also called the random phase assumption in the physics literature. Okay, so in either case, what matters is that you have that at time t equals to 0, or initially, you have the expected value of the modulus square of the Fourier modes is given by this n initial at k. So we call those well-prepared initial data. Okay, so this is what we mean by well-prepared, in the sense that this, we will see this is this, in other words, this means that the kinetic approximation that we will be after is satisfied at t equals to 0, which is a natural thing to assume. Okay, if we want to prove it at later times, it makes sense to assume it at time t equals to 0, or to put it at t equals 0. So as we said, the goal of the kinetic theory is to understand the distribution of the Fourier modes at later times, and the center quantity of interest is this expected value of the modulus square of the Fourier modes. Okay, this is the quantity for which we will try to get an effective equation. And the kinetic dynamics, just again drawing the analog with Boltzmann theory, appears in the limit when L goes to infinity, and alpha goes to 0, which replaces the limits n goes to infinity and r goes to 0 in Boltzmann's particle theory. Okay. All right, so what does this wave kinetic theory, which is also sometimes goes by the name of wave turbulence theory for reasons that I will explain later, what does it say? It says, this is what I will call the kinetic conjecture. It says that in the limit as L goes to infinity and alpha goes to 0, so this is the weak nonlinearity assumption or the weak nonlinearity limit, which is another reason why this theory is also called weak turbulence theory sometimes. So the effective dynamics of the expected value of the modulus square of the Fourier modes is given by the wave kinetic equation, which is something that I will write for you on the next slide. And this stands for or takes the role of Boltzmann's equation in this setting. So the approximation holds at a rescale time, which is the very important, the kinetic time, alpha to the -2. Okay, so namely what we expect is the following. We expect that at later times, the expected value of the modulus squared of u being the solution of the NLS equation, starting with random initial data, you just solve the NLS equation and evolve it. This is equal to n at time t over t kinetic. So this is the rescale time, and n would be a solution of the wave kinetic equation that you will see on the next slide, plus a term that, plus an error term that goes to 0 in the limit as L goes to infinity and alpha goes to 0. Okay.
The limit, so which is the order in which you take the limit L to infinity and alpha to 0?
Yeah, this is a non-trivial question that I will come back to.
Okay.
So this is essentially the question of the scaling laws, which we will in a couple of slides we'll be talking about that, if you don't mind. Yeah. That point is that there are more than one way to take it. There are some regimes. The short answer is that there are regimes of admissible ways to take those two limits, and we will talk about those regimes in a few slides. All right. So we will call this approximation over here approx, which is what it says that we can approximate the NLS dynamics at later times with the dynamics of the kinetic equation at the kinetic time scale, which is alpha to the -2. Okay, where alpha is, remember, is the strength of the number. Okay, so I owe you a statement or a description of this wave kinetic equation. So this was derived in the physics literature and has the following form. So this is the homogeneous form of this equation. It's dTn is equal to knn and n. So it's a trilinear operator here, this script k, which can be understood as a collision kernel, if you like. And the initial data is given by n initial of this wave kinetic equation. Now this collision operator is given as follows. So you integrate over xc1 minus xc2 plus xc3 equals to xc. So here I'm looking at knnn at xc. So it's an integral in xc1, xc2, and xc3, such that xc1 minus xc2 plus xc3 is equal to xc. Then we also have this delta function, which restricts the integration to this hypersurface xc1 squared minus xc2 squared plus xc3 squared minus xc squared. So here I should clarify that what I mean by this c sub beta squared. So here x sub beta squared is equal to the sum beta j xj squared, j being from 1 to d. Remember, because I twisted the Laplacian by those beta j. So that's what we mean by modulus sub beta squared. Okay, and then we have this nice integrand over here. Okay. This is the collision kernel. So this is the wave analog of Boltzmann's equation. Notice that this, again, this kinetic approximation features a passage from the time reversible NLS equation into the time irreversible wave kinetic equation. Okay. And one can also study inhomogeneous versions of this equation. So in which case you, instead of having dtn over here, you would have dtn plus xc dot grad x of n, where n becomes space independent as well. But we don't consider that problem here. Okay, so before we continue, let us talk a little bit about the literature related to this work. So the emergence of the wave turbulence theory, as far as I know, was roughly in the 1920s. First work was by Peirce. And since then, this kinetic formalism was generalized to many other nonlinear wave systems. For example, in the context of water waves, the kinetic equation there goes by the name of Hasselmann's equation. In the context of anharmonic crystal, it goes by the name of von Boltzmann equation. And also there are several wave kinetic equations that appear in plasma theory. And just like other kinetic theories, this is highly informative in applications in oceanography, in particular optics, crystals, and plasma theory. And one of the reasons this is quite useful in many applications is that it leads to a formal framework of turbulence for nonlinear waves. And this is why it's called wave turbulence theory. I won't be going into this formal framework of turbulence. This is still something that is not rigorously justified, but it is something that gives a particular importance to this theory. So formally, this wave kinetic theory gives us conclusions similar to those made in hydrodynamic turbulence. Mainly, you get out of this wave kinetic equations things that are power law cascade spectra. So these are analogs of Kolmogorov spectra of turbulence. So in this setting, these come as special stationary solutions of the wave kinetic equation that go by the name Kolmogorov-Zakharov cascade spectra. And those were discovered by Zakharov in the 60s. I mentioned some references here, and there was some work where those solutions were put on some more solid mathematical foundations. Okay. But still, there's much to be done here, particularly when it comes to the relation of those solutions to the NLS or the original microscopic system. This is something that's still open. So in terms of the mathematical literature, and influenced by this field of physics, the initial focus of the related mathematical research was on constructing solutions that exhibit growth of Sobolev norms. And here, Gigliola's talk was really the reference to this literature. So I only mention a very small collection of works. It's this list of contributors to this progress is highly non-exhaustive. So such growth is predicted by the Kolmogorov-Zakharov spectra. So this interest was really pioneered by Bourgain and Stafilani in the 90s, who started the question of the growth of Sobolev norm or obtaining bounds on Sobolev norms. And then there was several other contributions, some of which are mentioned here. Okay, so of course, the central question remains to give a rigorous justification of this kinetic approximation, or this rigorous whether can prove this approx in a rigorous way. And mathematically, of course, this gives you a precious insight into the generic long-time behavior of solutions of NLS or any other dispersive system where you can justify approx. And this includes questions related to energy cascade and growth of Sobolev norms, etc. Also, from a physical point of view, this is important in order to understand the exact regimes and limitations of wave turbulence theory. So hopefully those attempts at the works on the rigorous justification of theory could have an impact as well on the physical theory in terms of understanding its limitations and regimes. But before proceeding to discussing some of our results, let me start by mentioning some other works that deal with this or similar problems. So the first work that I know about that deals with a very similar question is the work of Lucanen and Spohn from around 2010, I believe. So they studied a similar problem, which is the time correlations of solutions of a discrete NLS equation at equilibrium. Then you can split the later development into two under two titles, if you like. So there's a stochastic setting in which you add a stochastic force to the equation. And so this is, for example, here there's work of Fau that considered a KdV type equation, and he was able to derive a linearized version of the kinetic equation. There's also works of Dymov and Cookson. So in the work of Fau, there was the type of forcing that was added is a Stratonovich type of forcing that sort of randomizes the angles without injecting energy into the system. Dymov and Cookson considered the case of a force dissipated system. So there was white noise anticipation. There was later work of Dymov, Cookson, Mayoki, and Ladutz that also had some partial results. So all those works have partial results in terms of justifying or deriving rigorously the kinetic equation. Here I should mention a new, very nice and deep work of Stafilani and Tran, which I believe appeared on arXiv this week, but we received a version of it a few weeks ago. So there they basically took Fau's model, but they got to the end result basically. So what they do is that you also have, so there's a high dimensional, they consider high dimensional KdV type equation with the stochastic forcing of the angles. So they force the angles in a, again, the Stratonovich type forcing of the angles. And then they derive the wave kinetic equation at the kinetic time under this forcing. They even have a conditional result in the case of zero forcing, the deterministic setting, and they verified this the needed condition for small perturbations of the equilibrium, which converge to the equilibrium in the limit that is taken. So in the deterministic setting, the first attempt at the full problem was in the work of Buckmaster, Germain, and myself, and Chata a couple of years ago. There we were in the setting of generic irrational tori, so we need a genericity assumption over there, and we were working in dimension d greater than or equal to 3 for NLS. We were considering NLS, the cubic, and the same equation that we have that I described. And in that work, we justified the approximation, but unfortunately only for very short times. So the times were still they were much bigger than 1. But they were still much smaller than the kinetic time. Okay, so we were quite far from the kinetic time scale in this first work. In a way, the importance of that first work is that it's sort of resolved a lot of the number theoretic issues that appear in this derivation. Okay, we'll talk about that a little bit later. So after this result, there was a following year, there was a work of myself with our first work with Yu Deng, and then around the same time, the work of Collin and Germain, which improved this approximation that we did in the first work, and actually removed the genericity assumption. At least we were working on general tori there for most of the result. So we improved this approximation considerably, all the way up to times. We were able to justify this approximation up to times that are L to the minus epsilon times the kinetic time scale, where epsilon is arbitrarily small. Okay, and we did this for some particular scaling laws. Okay, so let me just point out. So as I said before, we over here, at least in our work with Yu Deng, we were able to treat general tori over there and to distinguish according to the scaling law, which I will explain on the next slide, when is the genericity requirement needed and when it is not needed. So we developed we got to the understanding of that. So what are the scaling laws? So this is exactly answering the question that was asked to me in terms of the order of the limits that are taken. So this, we've already encountered an example of the scaling law. So the scaling law dictates the relative rates of the limits L goes to infinity and alpha goes to 0. So this is, we saw an example in Lanford's theorem, which is the Boltzmann-Grad scaling law. And a priori, you may consider various scaling laws of the form alpha equals L to the minus gamma, where gamma is ranging from 0 all the way to infinity. Okay, the case gamma equals to 0, you can think of it as corresponding to taking the limit L goes to infinity first, and following that by the limit alpha goes to 0, and vice versa for the case gamma equals infinity. Well, as it turns out that not all those scaling laws are admissible by the kinetic theory, or not all scaling laws give you a kinetic limit. Okay, it turns out that the admissible scaling laws depend on the shape of the domain, okay, or the aspect ratios of the torus. So for general tori, if you don't impose any generality assumption, then the only admissible scaling laws correspond to gamma between 0 and 1. Okay, you cannot study, or you do not get a kinetic approximation if you are in the scaling law alpha equals L to the minus gamma, when gamma is strictly bigger than 1. Okay, unless you add some generality assumptions on your torus. So if you add generality assumption on your torus, then you widen this range to gamma between 0 and d over 2. Okay, so these ranges are really dictated by a number theoretic condition that appears in this kinetic approximation that really does not allow you to get any results when gamma is bigger than d over 2 in the generic, for generic torus, or if you don't impose any conditions on the torus, which in particular the case for the rational torus, this is your regime, gamma is between 0 and 1. If I want to give a little bit more details for this audience about this, the key point or the first obstruction, there are several obstructions you observe if you're out of these admissible scaling laws, but one of the important obstructions is that in that case, your exact resonances overcome the quasi-resonances that converge to the kinetic theory. So in some sense, the part of the interactions that converge to the kinetic equation become sub-leading outside these ranges. This is what dictates those ranges. And it's not too hard to see them once you know the estimates on all the terms. Okay, so going back now, I can, now that we explained this notion of scaling laws, I can explain in more precisely those works of our first work with Yu Deng in 2019 and the work of Coulomb-Germain. So in that work, we proved the approximation, as I said, to times t less than L to the minus epsilon times the kinetic time scale only for two scaling laws, which correspond to gamma equals to 1 and gamma equals to epsilon. We call those two favorable scaling laws. We had partial results for other scaling laws and explained the obstructions for those other scaling laws. And contemporaneously, the work of Coulomb-Germain also gave the same result for gamma equals to 1. Okay, I should mention here also another work of Coulomb-Germain in 2020, which studied the problem over generic non-rectangular tori, and they proved a similar time range, this t less than L to the minus epsilon t to gamma. They were able to get existence of solutions, but not the approximation to the kinetic equation. Okay, so this is the literature before the work that I want to discuss today. The point is that all these works fail to reach the kinetic timescale T kinetic. We consider a full justification of the equation to be one that reaches timescales that are of the form delta times T kinetic, where delta is greater than 0 and independent of L and alpha. Okay. And this is precisely the content of our main theorem for today, which is a recent joint work earlier this year with Yu Deng. And so here we are able to give a full derivation of the wave kinetic equation. So again, let us summarize a little bit. So we consider the analysis equation on the torus TD of size L, or if you like on a box of size L with periodic boundary conditions. So we get in dimensions d greater than or equal to 3 and with generic beta. So the first, we have a result for non-generic beta that I'll discuss later. Assume that the initial data for the kinetic equation, which I denoted by n sub initial, if you remember, to be a Schwartz function. Of course, this is an overkill. We only need finitely many Schwartz norms to be bounded, but we don't care this time to optimize those conditions. And we take the initial data for the analysis equation to be well prepared, as we discussed a few slides ago. Okay, so we take, let us first take the scaling law alpha equals L inverse. And in this case, remember the kinetic timescale is always alpha to the -2. So in that case, the kinetic timescale is L squared. Then the theorem said that there exists a delta that is less than 1, which is fixed, and an absolute constant nu greater than 0, such that the following holds. Just as we want, the expected value of the module square of the Fourier modes is approximated by the solution of the wave kinetic equation rescaled at times t over t kinetic plus a term that goes to 0 as L goes to infinity. And the important thing is that this holds for times that are all the way up to the time delta times t kinetic. Okay. And we can also have the same proof extends to other scaling laws. So the same results holds for the scaling laws alpha equals L to the minus gamma, where gamma is smaller but close to 1, close enough to 1. And in that case, no assumptions on the shape of the torus is needed. You don't need this genericity assumption in that case. Okay, actually, whenever you have a result on, remember what I said here, in the case gamma between 0 and 1, this is a case that is admissible for all tori. So whenever you're working at a scaling law, alpha equals L to the minus gamma, where gamma is less than 1, then you don't need any genericity assumption on the torus. Okay, so this is our main theorem. We'll have some remarks about it on the next slide. So the interest in one scaling law of another, as we said, seems to depend on the physical context. So Hilberts pointed to us that there's a particular interest in the scaling law alpha equals L to the minus 1/2, which correspond to kinetic time scale equals L, which is the importance comes from the fact that this is related to the inhomogeneous problem. We think that this is something that should be covered under our approach, and we plan to study the scaling laws gamma between 0 and 1 in a future work. So this corresponds to having the kinetic time scale between 1 and L squared. Okay. So why is the scaling law alpha equals L inverse of particular importance? So the one that we consider over here. So this part of the reason why we considered it is because in this scaling law, the kinetic time scale is actually order of L squared. And as such, the result translates into a time one result on the unit torus. Okay. In particular, our result gives us an understanding of the dynamics of Littlewood Paley projection of the Gibbs measure in 3D for the 3D cubic analysis equation, which links our problem to the problem that Andrea was talking about in the previous talk, which is the still open problem of the invariance of the Gibbs measure for the 3D cubic analysis. And by the way, as Andrea explained to us, this is the only remaining unsolved Gibbs measure problem after their very nice recent works with Yu Deng and Haitian Yu. Okay, so a common difficulty of those two problems. So this problem is still open, this invariance of the 3D of Gibbs measure for 3D cubic analysis. The common difficulty between our problem and that problem is that both problems are probabilistically critical, as Andrea explained. Okay, and we shall explain a little bit below, possibly more briefly than how Andrea did it. So Andrea did a really good definition of this probabilistic criticality. And the point that I want to emphasize is that the problem that we are studying here is probabilistically critical. Okay. All right. So let me give a high-level overview of the proof. If there are no questions about the result. So the starting point of the proof is to perform a power series expansion of the solution, particularly to write it as in terms of its iterates. So what we do is that we write the solution as U0 plus U1 plus Un, and these are the Picard iterates or the Duhamel iterates of the solution plus a remainder. So each of those UNs is a multilinear Gaussian expression that can be represented by a tree with n branching nodes. So let me give a couple of examples so that to motivate things. So if you look at U0 here, so this U0 is nothing but the linear evolution of the initial data, which in Fourier space, if I want to write in Fourier space, this is given by basically U initial hat at k, if I filter out the linear propagator. And this will be represented by a tree, which is decorated by a frequency k. Okay, we say this is a trivial tree, which is one vertex decorated by a frequency k. So what about, let's look at the first iterate, U1. So U1 is given by I of U0, U0, U0. And this I is just the Duhamel integral. Okay, in Fourier space, I can still write it without much trouble. So this is sum over K1 minus K2 plus K3 equals to K. You have U initial hat at K1, U initial hat at K2, bar U initial hat at K3, e to the I omega t. So this is K3. And omega is just K1 squared minus K2 squared plus K3 squared minus K squared. Okay, and this will be represented by a tree which has one branching node, and we decorate it as follows. We put K on the root of the tree, and over the three leaves, we put K1, K2, K3. Okay, so what about U2? So U2, it's coming from, it's a Picard iterate. So you put I of U1, U0, U0. Okay, you might have this over here or over here. So it's the sum of those three terms. And again, I is the Duhamel integral. I won't try to write the expression in Fourier space because it's complicated, but I can draw down the tree, the corresponding tree in this case. So here you start with the tree that was over here, and then you branch out like this. By the way, over here you have, remember, we decorated by, in the previous tree, we decorated in such a way such that K is equal to K1 minus K2 plus K3. This is the admissible and important condition for the decoration. So over here, the decoration is as following. So you have at the root, you have K. So because we're looking at the Fourier transform at K. So this is UN hat at K, what we're looking at here. And this would be K1, K2, and K3. This would be N1, N2, and N3. And at each branching node, like you have that the parent, the decoration of the parent is given by this one minus this one plus this one. So over here, you have this condition holding for this branching node. And for this branching node, you have that K1 is equal to N1 minus N2 plus N3. Okay, and you keep on doing that for up to the nth iterates. Of course, the trees become more and more complicated, but each of the nth iterates can be written as a sum over decorated trees similar to this one or more, similar to this one or more higher order versions of this one. Okay, so this means that our solution, U hat of TK, can be represented as a sum of decorated trees, and the Fourier transform of the nth iterate is the sum of decorated ternary trees of scale n. The scale of a tree is the number of branching nodes of this tree. So this tree has scale 2 because it has 2 branching nodes. Okay, now as we said, we are interested in the expected value of U hat of TK squared. So we write U hat of TK squared as U hat of TK, U hat of TK bar. And we expand each of those in terms of trees. Okay, and this leaves us with taking, understanding the expectation of the pairs of trees, which we call couples. Okay, so this is a tree over here. And this is another tree. So for example, this tree might be coming from the expansion of U hat. This tree might be coming from the expansion of U hat bar. Now, because of the independence assumption on the initial data, remember the nth iterates only depend on the initial data. So they are multilinear Gaussian expressions because the initial data is given by each of the Fourier nodes has a Gaussian in it. So when you take the expected value of the product of two trees, you are faced with a quantity similar to this. This is the expected value of eta k1 up to eta kr, eta L1 bar up to eta L1 r, and then you have Kirchhoff laws here that tell you that the set k1 up to kr has to be the same as the set L1 up to Lr. What this corresponds for a decorated tree, it corresponds to the fact that the leaves of those trees have to be coupled or paired to each other. So here we denote the pairing of the two trees by the coloring. So this node is paired to this node, both of them are red. This node is paired to this node is paired to this node, etc. So you must have a full pairing of those trees. So the moral of the story is that if you're looking at the expected value of u hat of tk squared, what you will end up with is sum over couples of trees. Those trees could be arbitrarily, could be very large. And those trees, you have a full pairing between the leaves of those trees. These are the leaves of the trees. Okay. All right. So in order to understand this problem, you have two main enemies. The first enemy, which is the really serious one, is that there are order of n factorial such couples, because there are n factorial ways that you can pair the leaves. Okay. So if you have a couple of scale n, or if the scale of this tree plus the scale of this tree is equal to n, this is what we call the scale of the couple, then you have order of n factorial such couples or such pairings, okay? And this represents a major obstruction, as we will see, to the convergence of the power series expansion. The second enemy is the criticality. The point is that the n plus first iterate is only better than the nth iterate by a factor of delta, okay? Rather than by a negative power of n, okay? And this is exactly a reflection of the critical nature of the problem. And we'll explain those two things in a minute. So let's start with this second enemy, which is criticality. So you can understand this kinetic timescale as the longest timescale for which the power series expansion that we talked about of the solution in terms of the Feynman diagrams or in terms of the trees is valid, okay? In our previous work, in our first work with Yu Deng in 2019, we treated the full subcritical range, okay? So this is when you think of the proving the approximation on the interval t less than L to the minus epsilon times the kinetic timescale. This is really, you're being in the subcritical range. And the reason for that is the following. So in that setting, when you are only looking at this time interval, the n plus first iterate is better than the nth iterate by order of L to the minus epsilon, okay? And as such, if you look at the estimate of course, this is in caricature, the situation is much more complicated than that, but if you think of the nth iterate, then this would be order of L to the minus epsilon n, okay? Now, if you want this to be an error, if you want this to be less than L to the minus nu, for example, then it is enough to take n to be order of epsilon inverse. So in other words, it's enough to expand your solution up to a finite, do a finite expansion, which is order of epsilon inverse. Epsilon is fixed, okay, if you're working on this time interval, okay, in order to prove the approximation theorem. Okay, so this means that, and this is what we did in our first work, this means that it is enough to do a long but finite, or a finite but long expansion, which exploits the subtle combinatorial structures of the reefs. This is highly non-trivial, but it can be done at the level of the trees. Okay, partly because your expansion is finite and the length of the expansion does not depend on that. However, in our critical setting, as I said, the nth iterate is just better than the n-1 iterate by order of delta, not by an L-1. So at best, you have that the estimate for the un in caricature, in this setting, is order of delta to the n, at best. Okay, this is what I mean at best is that there are terms in this expansion that have size delta to the n, and there's nothing you can do about them. Actually, those are the terms that give you the kinetic equation. Okay, so and for this to be an error term at when n is large enough, you need to take, so for this delta to the n to be less than L to the minus nu, you need to take this n to be larger than log L over log delta inverse. In other words, you need to expand your solution up to a threshold that depends on L and diverges as L goes to infinity. And this is really what we do. We expand the solution up to the log Lth iterate and estimate the remainder. Okay, so this is what we will take. We'll take n to be like log L, maybe a power of log L, but that's it. Okay, so this is how we this is one way we overcome this criticality problem. Now the second enemy, which is the factorial divergence, is the really serious enemy. So here we have that if I look at the expected value of the nth iterate squared, this is a sum of two n factorial couples. Okay, so this is the number of those couples is factorial in n. Okay, and we know that some of those couples, as we just discussed, some of those couples have size delta to the n. We can write those couples down, and we can see that they have size delta to the n. Now, if all those couples have size delta to the n, then we are completely doomed, because we get delta to the n times 2n factorial, and something like that can never converge. So here, the toy problem or the caricature problem you should think of is that you have a power series expansion an t to the n. If an grows factorially, or then the radius of convergence is actually 0. So this brings us to the central strategy of our work, which is, I will formulate it as the following question, which is how we started thinking about this problem. The central question is the following: can one classify the couples into two groups, such that the group that saturates or almost saturates the worst case scenario estimates, which is delta to the n, that is the group that has size delta to the n or close to delta to the n, are relatively few. Say they are exponential in n rather than factorial in n. Okay, while the remaining factorially many couples satisfy much better estimates compared to this worst case scenario, which is delta to the n. Okay, so for example, can they feature a gain of power of L, which is sufficient to offset the factorial loss? Okay, the proof of this central question is really the heart of the problem. Okay, so the idea is that try to identify the largest couples. If we're lucky enough, those largest couples, there's only exponential number of them. There are few, relatively few. There are c to the n. And prove that the remaining couples feature a gain as powers of L, a sufficient gain in powers of L that I will explain in the next slide. So the first step in this strategy is to identify those largest couples. What are those largest couples? And so, of course, when you start working on the problem, the first hope is that those are exactly the leading couples that give you the kinetic approximations, that converge to the iterates of the kinetic equation. So one would hope that those couples with almost saturated estimates would be small perturbation of the leading ones that converge to the wave kinetic equation. And unfortunately, these are not the only ones. In fact, there are three families of couples with almost saturated estimates. The first one is what we call regular couples, and those are the ones that you can fashion easily, and these are the ones that you guess at first. These are the ones that converge to or some of them actually, the situation turns out to be complicated even with the regular couples. Their analysis is quite elaborate as well. So those regular couples contain inside them, as a subset, the couples that converge to the wave kinetic equation. They also contain couples whose contribution cancels out in the limit. Okay. The second family of couples that also give you almost saturated estimate, which is this delta to the n, is what we call irregular chains. I cannot, due to lack of time, I cannot draw them to you over here, but these are things that we even identified being a problem in our first work. So these also lead to almost saturated estimates. However, it turns out that they feature a major cancellation. Okay, And the last family, which has almost saturated estimates, is what we call type 2 molecular chains. Again, I have to apologize here. I cannot give you all the details on those for lack of time. And those, while they also satisfy almost saturated estimates, they have a favorable L1 in time bound, which makes their contribution acceptable. Okay, now the good news, so this is, these are the difficulties. The good news is that all those families are order of C to the n. There's only order of C to the n of them. Okay, and those lead to almost saturated estimates, whereas the remaining factorial in n number of couples all feature a gain in L. And this is the content of our main rigidity theorem, which arguably is the most important theorem of our work. So what this theorem says is the following. I'm just stating it in a, I'm paraphrasing it, given that I did not introduce all the needed notation. So the theorem says that if you perform a type of surgery on an arbitrary couple to remove all the regular subcouples out of it, all the irregular chains, all the type 2 molecular chains, these are, remember, these are the 3 types of trees that, or 3 types of structures, 3 structures that lead to saturated estimates. If you remove such structures from an arbitrary couple, there is a way to do that. Then we are left with a reduced structure whose estimate features a gain of L to the minus R, okay? Where R is comparable to the size of the structure. Okay, so if the size of the structure is R, then the gain in the estimates is L to the minus R. Why is this sufficient? This is sufficient because the number of possibilities of such structures is R factorial. Remember, the number of possibilities of a tree of scale n was n factorial or 2n factorial. So if we're talking about those couples of size R, their number is R factorial of them. And each one of them comes with a gain of L to the minus R. So what you have is, what you need is this, that this L to the minus R times R factorial is less than L to the minus mu. This is the error. This is our gauge for the error. And this is indeed true if you take R to be less than logarithmic in n, which is the case. Remember, we are expanding only up to order n, which is logarithmic in n. Actually, this holds true even for larger than, for R, even up to L to the epsilon, but this is more than sufficient for us. Okay, and this is why, this is how we control those factorially many couples. Okay. And the proof of this rigidity theorem is actually quite sophisticated. It involves recasting the problem of counting couples into counting another family of combinatorial structures, which we call molecules. I'll show you an example of a molecule on the next slide. And after you recast this problem in terms of counting molecules, the way we do it is by running something akin to a computer program, and like we follow an algorithm. Then this algorithm reduces the complexity of the molecule at each step and allows us to, at each step, to count those molecules effectively. So what do I mean by molecules? So here I write down the couple that you have seen a couple of slides before. So these are, you have trees, and the leaves of those trees are paired. Now, the reason why you need this structure of molecules is the following. The fact that the leaves of the couples are paired to each other, this is a very non-local property. You can have a leaf over here that is paired to another leaf in very far away in the tree or very far away in the couple. So in order to count things effectively, one needs to make this pairing structure local. And this is what the molecules do exactly. So this is a molecule over here. And these are the atoms in the molecule, and these are the bonds. Okay. Each atom in this molecule corresponds to a local family over here. So this atom corresponds to this local family, which means that corresponds to this branching node along with its 3 children. Okay. And this node, for example, this 3, I believe, corresponds to this one. So this is 1, this is 3, etc. And the bonds between the atoms corresponds either to a pairing of the leaves between, for example, you have a pairing of, between this atom and this atom, you have those two leaves being paired, which corresponds to drawing a bond at the level of the molecule. Okay, so this is due to lack of time. Probably this is more confusing than not, but essentially this is the right way, if you like, to count the number of such couples in an effective way, and in order to gain to see this gain that we want, this L to the minus R gain on those couples. Okay, so finally, okay, I'm out of time. So the analysis of those couple families, each that I mentioned requires a different genre of argument. So, for example, the regular couples require their own argument. The irregular chains require their own arguments. Type 2 chains require their own arguments. And those arguments range from combinatorial constructions to analytic ones. And also to, you need to do some number theoretic ones because you need to justify the discrete to continuous approximation. Okay, because you're starting with in frequency space, you're starting with a discrete frequency space, and you want to end up with a continuous equation, which is the wave kinetic equation. And once this picture is made clear, the estimate on the remaining term is relatively easier. I don't have time to go into it, but it can be derived. Essentially, it can be reduced to the analysis above. All right, so that's all I had for today. Thank you for your attention.
Thank you very much for your talk. Is there any question or remark?
I have one question.
Yes, go ahead.
So, no, very nice work. I mean, sort of impressive. I mean, I've seen such kind of diagrams before. I mean, it's a very difficult job. No, but I have a real question. I mean, could you do the same thing for the discretized nonlinear Schrödinger equation? You see, I mean, this combinatorial structure and the tree structure, all these things, you know, they are sort of identical. I guess the main difference is that when you look at the discrete case, you have, you know, your case space is compact, I mean, which makes life better, but your dispersion relation is not k-squared. And so right. I wonder, you know, whether you could comment on, you know, whether this could be done on a lattice or
I think that the approach is robust enough to handle the lattice. The exact dispersion relation being k-squared is okay. So there's, I guess I'm not sure if this is your question or the first place where one is afraid that the dispersion relation, changing the dispersion relation might ruin things is in terms of the number theory. But it turns out that we go back to this fundamental issue of scaling laws. Okay, if you are taking a scaling law for gamma between 0 and 1/2, then the role of the dispersion relation being k-squared is not that important. Okay, so
yeah, but I want to do kinetic limit. I mean, so you see in our work, I mean, we had a lot of problems since we were on the lattice, we had a lot of problems with the dispersion relation.
Right.
You know, but we had to do estimates which were actually quite delicate. I mean, you know, they sort of look simple, but you know, these are sort of rather complicated Fourier integrals, and so it's difficult to do them. And of course, you know, if you replace, if you put k-squared, I mean, then you have a lot of simplification. Actually, so just
yes. So I guess what I'm saying is that I suspect that if you choose the right scaling laws, particularly the scaling laws
that are scaling law. I mean, there's only, you know, I want to do the kinetic limit, right? I mean, so there's only one scaling law, I think.
In that
derive the kinetic equation, right?
I'm sorry?
I want to derive the kinetic equation, so there's only one scaling law in some sense. I mean, it's you know,
yeah, maybe in the discrete setting.
Same for the discrete. I mean, it's the same thing, right? I mean. Scaling. I mean, I want to put T kinetic is alpha to the -2 or equal to L squared, right? I mean, that's the same.
Right. Yes. I mean, I guess the question is that yes, you will have there might be some more difficulties at the level of the dispersion relation, as it was the case in your in your work, but I suspect that the kind of combinatorial analysis should go through, or parts of it, of course, not directly, but I think there's something like that should be possible for the discrete, in the discrete setting as well.
I see. Okay. No, but it's beautiful work. I mean, I'm sort of very beautiful.
Thank you.
Any other questions? I turn the room now. Yes.
Yeah, I have a question.
Yes, go ahead. Go ahead.
Okay. Have you studied scaling laws where the lattice, where you resolve the lattice structure better? Meaning you have your effective equation which integrates over R, but do you have scaling regimes where you see other effects due to the underlying lattice?
Yes, I mean, in some sense, these are the scaling laws that I excluded, because when you start seeing something that is too much dependent on the underlying lattice, then you probably are not converging to the kinetic limit in the end. So,
like we studied this in the context of Boltzmann, and like you do get collision terms, but like they look just different than this main term that you have, but they interfere with your main order term. And that has to do with like some time-dependent coefficients that appear in there that you can either have or not, dependent on rationality of certain expressions.
So I think that there is a similar thing that appears over here that I can write for you, maybe just to make sure that we're talking about the same thing. So if you do the expansion of your equation, if you do the expansion of, as I said, u equals to u0 plus u1 plus etc. And if you even look at that first iterate, u1, so this looks as sum over k1 minus k2 plus k3 equals to k, okay, e to the, sorry. Then you have, let me call the initial data ak1, ak2 bar, ak3, e to the I omega t. Okay, now this has basically some resonant interactions which correspond to k1 minus k2 plus k3 equals to k, and omega equals to 0. Remember, omega was k1 squared minus k2 squared plus k3 squared minus k squared. Okay, and then you have the interactions for which omega is essentially less than 1 over t. Okay, again, this is a caricature, but these are the interactions that end up converging to the kinetic equation. Now, there is a regime where these dominate these. Okay, the exact resonances dominate. And the exact what is the regime for which the exact resonances dominate? The quasi-resonances. This was what you can call quasi-resonances. Okay, and these are the exact resonances. This depends on the rationality property of the torus. Okay. Okay, so because if you are on a rational torus, you have a lot of exact resonances. If you are in an irrational torus, you have very few or much fewer exact resonances. And the regime that I told you about, the admissible, what I refer to as the admissible scaling laws, is exactly something that could be read of between those two. Exactly the regime where these dominate, the quasi-resonances dominate the exact resonances, and this depends on the rationality properties of the torus. Okay, but again, so the point is that if you are working in scaling laws such that alpha equals L to the minus gamma, where gamma is between 0 and 1. Okay, so this means that the kinetic time scale is between 1 and L squared. Then you always have that those quasi-resonances dominate the exact resonances, no matter what is the shape of the torus. They always dominate them, no matter what the shape of the torus. Okay, if you impose irrationality assumption on the torus, then the quasi-resonances dominate the exact resonances on a larger regime. So you can treat more and more scaling laws in the irrational case. But on in the rational case, there's still this window of scaling laws that are admissible and for which the quasi-resonances dominate all the other interactions, and as such, you can prove the kinetic approximation, because these are the ones that converge to the kinetic equation. Okay, is this what you were talking about?
Yeah, I just think that like, or for us, like it was also interesting to consider the regime where the resonances are also relevant.
Yes, we have studied these problems earlier, before we sort of as a precursor to studying the wave kinetic limit, and we studied the regimes, some of the regimes in which in the deterministic setting where those things dominate, and in that case you get an effective equation that is different from the wave kinetic equations, what we called continuous resonant or CR equation in that setting. We did that a few years ago, starting with work with Fau and Germain, and then with Buckmaster, Germain, and Chata. So we did, there are some regimes, particularly deterministic regimes, where this thing dominates, and you can formulate limits of this, and yeah. But it would be definitely interesting to find out a way to put yourself in a regime where they both of them contribute, but then you have two very different time scales, two things that operate at different scales. Quite complicated to me.
Is there any other question?
I have a minor question, more like a simple question. So, what is 1/t actually?
T is the time interval of your.
So in the scaling, it should. Can you express that in terms of alpha for me?
Yeah, T would be sort of. So if you want the kinetic time scale, if you want to get to the kinetic time scale, this is 1/alpha squared.
Yes. Okay. So that should be just. Okay. Okay. Okay.
It's yeah, it's a bit involved, but yes. So
so one of the question, it's probably more of a natural question, is so here the starting point is of course with many body. No, not many body. Sorry, with a nonlinear Schrodinger. Okay, then you do this. But then the natural question is, of course, can you start with a many body system, and then do this? So I every single time I try to look these things up, as everyone's starting point is always the nonlinear Schrodinger equations. So I'm more interested in, because I know you can probably I think there are certain literature that you can start with, like the many body.
Yes, yes, I've seen some of that literature where people start with the quantum many body problems, and there's a kinetic limit that also over there, very interesting, that
but
one
how
could study to justify, but I didn't, I don't know. I cannot say in a precise way the intersection, how much intersection does this have?
I mean, in the quantum case, the tree structure which you described them is very similar.
Yes, yes, the tree structure indeed is very
similar. So, you know, my hope would be that, you know, if you sort of perfection your system, maybe you can also study the many-body quantum mechanical case.
Yes, yes, we have that in mind. Yeah, yeah.
I mean,
actually, maybe there's one, because the reason why I asked is there is one question about H bar scaling, like the Planck's constant. Okay, that so I was thinking about a many body bosonic system. Okay, then around the condensate you have this nonlinear Schrodinger equation But at the same time, the fluctuation about this is kind of related. I think the corresponding wave kinetic equation is the 3-phonon equation or something like that. There is some type of equation, and to derive it, what I can see is there's something related to H bar scaling, which I'm not I don't know anything about this, but so when looking at all these work, when you look at low frequency modes, that corresponds to imposing a condition. To me, it seems like it's in quantum setting is you're imposing a condition of looking at momentums that scales, that doesn't grow inversely proportional to how the Planck constant grows. So there's some condition imposing there. So, but I haven't been able to find the correct way of articulating this, and I haven't seen other people articulate this point.
Can I suggest that we postpone the discussions to the breaking rooms, because here we have to be at 7 sharp to dinner, otherwise.
Okay, sorry.
Yeah, but we will open the usual breaking rooms. I strongly recommend that those who are interested attend the rooms in order to continue the discussion. And otherwise, we are very pleased to thank Zahir for the very nice talk, as well as all the speakers of today. And we meet tomorrow at 3 local time, right? Thanks a lot.